A couple of things we want to do in this lesson. One is we want to talk about transformations of exponential functions. And, to be fair, this is one of these things where I probably don't need a special lesson on transformations of exponential functions, because you should know what this graph looks like. I mean, you need more details, right? You need to know if c is between 0 and 1 or greater than 1. But you should know what it looks like, and you should be able to apply a, b, h, and k to it. That's what the first part of this lesson is about. The second part, though, is continuing to solve problems involving exponential growth and decay, which are a little bit different than the previous ones, or can be. So to begin with, if we take the function f of x equals c to the x, and we transform it into y equals a f of b bracket x minus h n bracket n bracket plus k, what is the equation of the function? And if I were to retype these notes, and I make a note for myself for next time, I probably would have written g of x here equals instead of f of x. And I'm going to make that modification right now. So I'm going to say that g of x, the new function, is a multiplied by f of b bracket x minus h n bracket plus k. So I guess I'm going to do something here that I don't think I need to. You should understand that function notation. But if f of x is c to the x, and I asked you to tell me what is f of 3, you would say it's c to the 3. Correct? That's all f of 3 means. It means take f of x, and wherever there's an x, change it to 3. If I asked you to determine f of diamonds, then it would be c to the diamonds, right? It doesn't matter what that input is. You put it in for x in the function. Well, the input here is this, right? So that f of that yellow thing simply means take f of x, and wherever there's an x, change it to that yellow thing. So again, I think this is, obvious is maybe the wrong word. I think this is something that I would expect everybody to know anyway, but I've just taken an opportunity to explain it. So this will be a multiplied by, and I just like to put a little multiplication sign there, c raised to the b times x minus h, and then plus k. That's the equation of the function. And the reason why I'm asking us to do this in the warm-up is so that we can recognize that structure as being something that is a transformation of c to the x. This is why I prefer to use c for the base here. Okay? Because in this, there's a b. Now, there's an issue with that, because when we go to your formula sheet a little later, I believe it's a b for the base. Okay, we'll get to that. Does anybody have any questions about this warm-up? Okay. So, describe the transformations involved here. Based on the warm-up, you ought to be able to figure out that this transformation has a parameter a value of 2. That number 3 in both f of x and g of x is not a parameter. Well, I mean, I guess it is a parameter, but it's not an ABHK parameter. It's the base of both functions. The value of the parameter b is equal to 1, because there's a 1 in front of the x minus 4. The parameter h is 4, and the parameter k is 15. Again, to be fair, I think this is a question I could have asked you on day 2 of the course. What are the transformations involved here? Maybe it would be a little bit of a problem on day 2 of the course, because you might not be as familiar with something like y equals 3 to the x yet. But you ought to be able to extract a, b, h, and k out of there and say that there is a vertical stretch by a factor of 3. Sorry. There is a vertical stretch by a factor of 2. don't abbreviate stuff on a written response. We've just been away for a week, and I want to remind you of a few things. You would probably write vertical stretch by a factor of 2. There is no horizontal stretch. There is a translation of 4 units to the right. There is a translation of 15 units up. Are we okay with that? All right, B. Well, now what we're going to do is we're going to sketch these 2 graphs. And I think what I would like to do is just put the points down first. We can talk about how important it is to draw the smooth curve afterwards, but I want to teach you the math first, and then we can practice the skill of actually trying to draw a curve that goes through these points. So what does y equals 3 to the x look like? Well, 3 to the x will have an asymptote on the x-axis. Y equals c to the x, in this case y equals 3 to the x, will always have an asymptote on the x-axis. We also know from the first lesson that the y-intercept of c to the x, so what I'm talking about right now, everybody, is the 3 to the x one. And I'm going to use red as 3 to the x. We also know the y-intercept will always be 1. And this is why I'm not too keen on sketching this, because I can't even locate 1 precisely. Are you with me on this kind of my apprehension in sketching this? Okay. And we've learned, and this is maybe the most important part of an exponential function, that the base tells you what is happening to y regularly. So every time x goes up by 1, y in this case will be tripled. So it will go from y equals 1, move over 1, and it will go to y equals 3, because 3 times 1 is 3. And we triple 3, and we get 9. And we triple 9, and we get 27. So there's no need to say to yourself 3 to the 3 and 3 to the 4. If you take this approach, you're simply tripling the previous value of y. And can you just confirm, I'm pretty sure, that when I triple 27, I get 81? Okay. Can I fit 81 on there? Well, I can't. So that's it. That would be y equals 3 to the x. So what are we going to do with that? We are going to stretch all of these points vertically by a factor of 2. Then we're going to shift them 4 units to the right and 15 units up. But I want to make a point to you, everybody. That this asymptote is part of the graph. I mean, it's not maybe really part of the graph, but it's a feature that the points are all drawn relative to. So if I'm going to end up in the end translating this 15 units up, then what that means is that the asymptote will now be up at y equals 15. Does that make sense? It's kind of like what we did with trigonometric graphs, like sine and cosine, where if d, we use d instead of k, but if d were 20, then we would shift that midline up to 20, and the maximum would be the amplitude above, and the minimum would be the amplitude below. Let's keep that in mind as I start to plot these points. We know that we're going to take this point, and my asymptote got moved here. We're going to take this point and double the vertical distance. So the original point on 3 to the x is at 1. I double 1, I get 2. And I want you to note that this point is at y equals 2, but more importantly, it's 2 above that asymptote. Okay? I'm going to shift it 4 units to the right, and then I'm going to shift it 15 up. Well, if I shift it 15 up and the y-coordinate is 2, the new y-coordinate will be 17. Yes? Well, where is 17 going to be? It's going to be 2 above that asymptote. And I guess what I'm getting at is maybe it's possible for some of you to start plotting these points in reference to the asymptote. Okay? Let's do another one. So this point is at y equals 3 and x equals 1. I double 3 and get 6. I want you to notice it happens to be 6 above that original asymptote. I'm going to shift it 4 to the right, 1, 2, 3, 4, and then up 15. Well, if I take 6 plus 15, I get 21, and now it is 6 above that asymptote. And, you know, I guess what I could be doing is even going so far as to say this point here is going to be 6 above the asymptote and 1 to the right of the previous point. You know, I could take that approach. Or I could do it singularly, point by point. Let's just do 1 or 2 more. I don't know that we'll be able to do 2 more. This point is at 9. I double 9 and I get 18, which will be approximately there, which is 18 above that original asymptote. I move it 1, 2, 3, 4 to the right, and now I move it 15 up. It has a y coordinate of 18. 18 plus 15 is 33. So it's going to be up at 33, which will be here. And you'll notice it's 18 above. So now comes the part where I'm always apprehensive about this because I have a horrible time drawing on a vertical surface smooth curves. But I'm going to give it a shot. And I wouldn't push my luck. I would just stop there and put an arrow on the end of it. And if I had a really fine way of writing, I would put an arrow on the end at the bottom as well. This one looks like that. For g of x, we're asked for the equation of the horizontal asymptote. Well, that will be y equals 15. The y-intercept, which we'll get to. The x-intercept, there is none. The domain and range. Hopefully you can see the domain is any real number. And you can't do anything to 3 to the x to change that fact. You can't. What is the y-intercept? Well, can you see, just look at this graph, look at the brown graph and the brown asymptote, that the y-intercept is going to be very, 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 very close to 15. But it's going to be a little bit above 15. Am I alone on this? That if you extended that graph, it would just get closer and closer to the asymptote, and it's going to cross somewhere, you know, there. I mean, even closer than that. I can't do justice to this. But how do we algebraically find a y-intercept? We take the function, and we replace x with 0. So it was 2 multiplied by 3 raised to the 0 minus 4 plus 15. Go ahead and use your calculator for me, please, there. I can't do this in my head. We want a fractional answer. Melanie's on it. She's going to tell us.
15.0246.
And can you convert it to a fraction, please?
1,217 over 81.
1,217?
Over 81.
Over 81. 1217 over 81. And just read back that. Anybody else get that? Okay, just read back that decimal value.
15.0246.
So 15.0246. It's a little bit above the asymptote, which is to be expected. Any questions with C? Okay. Describe the transformations involved here. This one we're not going to bother graphing it, I don't believe. We just want the transformations. Well, there is a vertical reflection. I guess I should do this. And I'll give you a moment or two to reflect on that. No pun intended. Are we in agreement on the values of those parameters? Okay. So since A is negative, there's a vertical reflection. There's also a vertical stretch by a factor of 1/2. There is a horizontal stretch by a factor of 5. So, I don't think we really need to do this, but just the next 2 months are going to go by really quick. The next thing you know, you're going to be staring at the diploma exam. So it's never too early to kind of review things. What does that mean? A vertical stretch by a factor of 1/2 means things get half as close to the x-axis as they were. Horizontal stretch by a factor of 5, which of course is the reciprocal of b, means that. There is no horizontal translation, but there is a shift of 5 units downward. I think we're okay with that. All right. I have this highlighted, and I cleaned up this presentation midweek last week, so I can't remember for sure. It's probably because you don't have h of x there. But I'm referring to all of this information for h of x. What is the equation of the horizontal asymptote? Well, it will be at y equals -5. The equation of the horizontal asymptote of, say, 3 to the x is y equals 0. So as soon as you translate y equals 3 to the x up or down some number, that number, along with the up or down, becomes where the new asymptote is. What is the x-intercept? Well, let's just think about this for a second. And then algebraically, I'll demonstrate that there is no x-intercept. The asymptote is down at -5, but there was a vertical reflection first before things were shifted. And the vertical reflection means it went from doing this to doing this. And I've stretched it at the same time by a factor of 1/2. So when I move that down, it's going to be below the asymptote. It cannot cross the x-axis. So there is none. And, I'm debating right now whether I will demonstrate algebraically to you why that's the case or not. We'll just leave it alone. What is the y-intercept? Well, the y-intercept will be h of 0. So it's going to be -1/2 multiplied by 3 to the 1/5 times 0 minus 5. Well, 1/5 times 0 is 0. 3 to the 0 is 1. 1/2 times 1 is 1/2. 1/2 minus 5 is -4.5. Did anybody do that on their calculator? Can you confirm that that was right? Okay, I see one person that confirms it. By the way, you could graph this and get this information as well. The domain will be x as any real number, and the range will be y is less than -5. So the previous question had us do a graph to help us answer these questions. Now it's kind of moved away from that. Any questions with B? All right. What about this? So let's move away from a graph, and let's even move away from knowing the specific values of the parameters, including the base, which I'm using as b here. What is the equation of the horizontal asymptote of this function? It's going to be y equals k. It doesn't matter whether k is positive. If k is positive 8, then the asymptote would be shifting from the x-axis up 8, landing at y equals 8. If the asymptote is -3, then the asymptote is going to shift from the x-axis 3 down, giving its new location y equals -3. So the asymptote will always be at y equals k. What will the y-intercept be? Well, let's find out. Listen, I don't want you to walk away from this particular example saying, I need to memorize the result of this. Because I could give you a different function up top. I could put, I could do this. I could put, I'll use g of x, and don't write this down because it's just something that I'm making up. I could write that and say, what is the y-intercept? And it's going to be found by putting x equals 0 in and seeing what you get. So there's nothing special about the answer we're going to get here. On the other hand, I think there is something special about this. This is a fact. I mean, I suppose I could change this to 5k up here, and the answer would be y equals 5k. But you get the idea that that's a pretty important idea, that the horizontal asymptote will be where k is. So let's simplify this. What do we get? We get f of 0 is equal to a times b to the negative h plus k, which would probably be written this way. 0 minus h is negative h. B to a negative exponent is the same as b to the positive exponent in the denominator. And you're going to be getting lots of practice for the remainder of this unit dealing with exponents and exponent laws. Domain, any real number. And what about the range? Can we answer the question definitively about what the range is going to be here? So if you say yes, I'm going to put you on the spot and say, what is the range then? Noah? Okay. Does it have to be? And those are your words. And I'm not, I mean, I guess I am kind of putting you on the spot. You said y has to be greater than k. Good. If a, and I'm sorry I interrupted you there, and I ended up not hearing what you said. If a is what? So what about this one?
Oh, it has to be greater.
Okay. If a is a greater than 0 or y is less than k if a is less than 0, right? Because if it's less than, if a is negative, then the thing has been reflected vertically before with the shift. That vertical reflection lands the entire graph below the asymptote at y equals k. All right. So if you take a look at this thing, and we're going to get practice with this today and tomorrow and maybe even the next day. This is different than what I started today's review with. What I started today's review with was this. I said the quantity growing or declining is a times b to the t. And I said before we got started with this lesson, this is a basic application formula, and it only works if the change is happening annually or daily, where really what you're putting in up here for t, and I want you to think about this. This is a really important idea. What you're putting in for t in this equation, if the change is happening, say, annually, you're putting the number of years. But what that means is you're putting the number of times b is applied as a change. So if we're talking about the truck declining by whatever it was, 9.3%, and you put in 8 for t, it's declining by 9.3% 8 times. This t that I've got the arrow pointing at is how many times the application occurs. Okay? That is all that is important with an exponential change, is the exponent is how many times it happens. So now we have something different. we now have another parameter, and it's P. And what P is, so let's go through this. Y is the quantity growing or decaying, and T is the elapsed time. T is no longer going to be how many times B happens. It's just the time period. Shouldn't have said that. It's just the time. A is the initial amount, which we said it was before. B is what I call the factor of change. So with the truck, it was 0.903 because it declined by 9%. 9.7%, whatever the number was. With a population growing at 4%, B would be 1.04. But P is the period of time it takes to happen. That's why I didn't want to use the word period earlier. So let me just demonstrate something to you, I guess, before I do. These are clearly variables. These are parameters. Okay? And this is on your formula sheet. If I told you that the population goes up by 4% every 0.5 years. I'm going to use that as an abbreviation rather than A. And I said that the time is 10 years. Just think about this. Forget about the formula. The population is going to grow by 4% every half year, and it's doing that for 10 years. How many times will the population grow by 4%? 20, right? Go ahead and take T, which is 10, divide by 0.5, which is the period. You get 20. So this period, this P up here, we use P for period here, this P is there so that it converts the time to a number of applications of the base. Let's take a look at the examples, then I will show you on your formula sheet where it is. Am I going too fast right now? Okay. So a radioactive element of americium is used in household smoke detectors. This particular flavor of americium, americium-241, has a half-life of approximately 432 years. The average smoke detector comes from the factory with 200 micrograms of americium. Okay. That symbol, if you've taken Physics 20, you should know what that symbol means in this context. It's a metric prefix. It's like centi would be 10 to the negative 2, or kilo is 10 to the 3. Micro is 10 to the negative 6. It is a Greek letter. It's pronounced mu. Okay? How many of you remember this from, say, Physics 20? You might have used it with a coefficient of friction. Back in, this would have been the summer of 1990, I was backpacking around Europe, and we stayed in Greece for a long time, like 3 weeks, on an island, Piso Levadi. And this was a picture I took of the cat that would just hang around and stare at us. Don't get ahead of me. Would just stare at us on the balcony when we were having an afternoon cocktail and looking out at the Aegean Sea. And this cat, just for days and days and days, all it did was it just stared at us, and it would move every now and then and lick its paw. And it never said anything. Very friendly cat, but kind of intimidating. And then one day, it's a Greek cat, right? Oh, come on, you guys. I work. You know how long it takes me to think of some of these things? Okay, let's move on then. The radioactive element has a half-life of 432 years. Who remembers what that means? Eric.
In 432 years, it'll be half of itself?
Right. In 432 years, it will be half. And it's just like the money thing I talked about before. It isn't that your smoke detector has 200 micrograms of this isotope, and then it has that same amount for 200 years, and then at the end, or 432 years, and at the end of that 432 years, it all of a sudden gets cut in half. It's declining continually. But what this means is that the period is 432, and the base is 0.5. It means that every 432 years, that's the length of time it takes to happen, you're going to have 1/2 of the substance remaining. For you people that are, well, in physics now and going to be taking physics, you haven't learned about half-life yet, but what you will discover or be taught or learn is that it doesn't just disappear, it changes into something else. It undergoes what's called a radioactive decay, and it might become another isotope. Well, it will become another isotope. So here's the formula. Let's get our formula sheets out, if you don't have it out in front of you, and just locate where it is. I'll bring it up here as well. I may have to go over there and move it. Yeah. It's always nice just to familiarize yourself with where things are. It's on the left-hand column, midway, 2/3 of the way down. It's underneath all of this logarithm stuff that we're going to be learning about in this unit, and it's above the general form of the transformation. It's called the growth and decay formula. We tend to use y for the quantity growing or decaying, and t for the length of time. So those are our variables, and the parameters are a, b, and p. So we use b here. In the earlier part of the lesson, we used c because we were talking about b being a parameter that deals with a horizontal stretch. We've talked about this before. You have to get used to so much in terms of these letters. P is the period. If we go back 1 unit, the period is k for a trigonometric function. If we go back to the beginning, k is not the period, it's a vertical translation. Just get used to it. You gotta sort all this stuff out in your head. So this is the formula. We do need to know what A is. A is the initial amount. And you'll get enough practice that this should become natural to you. So the initial amount is 200 micrograms, which means we've got the 3 parameters. We now have a formula. Y equals A times 0.5. There's nothing wrong with writing 0.5. You can put 1/2 if you like. Raised to the t over the parameter p, which is 432. So the question now is, if I told you that the smoke detector becomes defective when the amount of americium drops below 75 micrograms, how long is it good for? Well, I hope you see it's going to be good for at least the rest of your life, because it takes 432 years to get cut in half. But this is the question. So we have to put 75 in for y. And solve that equation for t. And you are not equipped to solve that equation for t yet, algebraically. There's a way to do it, but you need to know how logarithms, well, what logarithms are and how logarithms work. The only way that we can do this at this point is to use our graphing calculator and find out where these two functions, I mean 75 I guess is a function, it's a constant polynomial function, where they're equal to each other. This is not anything you would ever do on a written response. Okay, you cannot do it this way on a written response. Well, you can, you just don't expect to get very many marks. So y is 75, and then, whoop. Okay. 75, and then 200 multiplied by 0.5 raised to, we are definitely going to need a set of brackets around the t over 432, because if we didn't, it's going to raise it to the t and then divide the whole result by 432. A little bit of common sense here. We know that it starts with a value, it being the amount of material, starts at 200, and it declines in value, so it's going to go down. I don't want to turn this into a physics lesson, but it's going to take 432 years to get cut in half to 100, and we want to go to 75. So it seems reasonable to me for my window setting to go up to maybe 600. I mean, past 432, because 432 will take me to 200, to 100 from 200. And then, I don't care what the scale is, 100. Let's go 0 to, well, I could get away with 200. I'm going to go 220. So there's 75. Here's the amount of americium. Ooh, I almost didn't make it. When I said let's go up to 600, I thought I was even going to say it, and I'm sure that will be enough. I think it is, but I'm going to change that to 700. Looks like it's going to be a little less than 600 years. Go to your intersect option of your calculate menu. No, it's a little bit more than 600. 612 years. 611 years. If you knew something about logarithms, you don't try to decipher that. I mean, a couple of you I know have been doing some extracurricular math involving logarithms, and you understand what's happening there. Maybe. I mean, I didn't show any work, but I just did it. Once we do understand about logarithms, there's an expectation that you can do it algebraically. Okay? And you're not going to be, not too many of you will rise to the level where you can just look at it and do what I just did. You have to write stuff down. Okay? All right, let's take a look at one final example. And this is the same kind of as the one that Faye had asked about. We should already know how to do this. And in fact, since it's an annual growth rate, when we talk about, and I put it here anyway, even though we should know how to do it, because it's an annual growth rate, our formula becomes this. Because if we're talking about a percentage of growth of a rare stamp, and it's an annual growth rate, the period of time it takes for that percentage to be applied is 1. And I guess what I'm demonstrating to you is that sometimes we can just revert back to what we learned in the last lesson. If it's an annual thing, you don't need to worry about over the period. The only thing we know here in terms of the parameters is that A is equal to $100. We do not know the value of B, but I hope you would agree that if it says determine the annual percentage growth rate, B contains the answer to that question. If we knew what B was, we could figure out what the growth rate is. So it's a missing parameter problem. We have y equals 100 times b to the t, but we also know that after 15 years, the value of the stamp is $4,500. So we can load that in and have 4,500. Is equal to 100 times b to the 15. So b to the 15 equals Not a genius, but I think that's 45 when we take 4,500 divided by 100. So what do? We could take the 15th root, or what we could do is say, I'm going to raise both sides of this equation to the 1/15th. And just get b equals whatever 45 raised to the 1/15th is. .289, we'll say. You know, and some people will record that as an answer. And even if I give this on an exam, even after having this discussion, some people will put 1.289 as an answer, numerical response. Some people will say, no, 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 it's 128.9%, so they'll round it and they'll say it's 129%. The answer to the question is it's 28.9%. Because you're asked for how much it grows by, and it starts off at 100%. So if we take 128.9% and subtract the 100% that it's growing from, we get a growth rate of 28.9%. There are a number of questions. These are exam-style questions, multiple choice, numerical response, that are on the following pages, probably starting at page 10. Well, the next page, whatever the page number is. So get to work on that, please. I need to take my attendance, and then I'll come around and I'll just double check on how the lesson went for you.